Hi, and welcome to chapter 6. So this chapter is a very large chapter, so I'm going to cut it into little pieces. So hopefully it doesn't feel too overwhelming. It is a lot. It's like 108 slides. So work through it piece by piece. Let me know if you need any help or if you get confused or lost about anything. This is a very, very, very important chapter for this course. So in chapter 6, we're going to study chemical compounds. So first, it's helpful to think about if we're talking about a compound or an element. So for example, sugar, which is the chemical name is sucrose, is carbon, hydrogen, and oxygen. But it has a specific combination of carbon, hydrogen, and oxygen that is also chemically bonded together. So it's not the same as if it were just carbon and oxygen and hydrogen put together, because oxygen and hydrogen are gases and carbon is like, what's in your pencil lead. So sugar is definitely different than your pencil lead. So it's definitely not the same as its elements. It is put together in a compound and now has totally different chemical properties. So some kind of chemical reaction happened to make the carbon, oxygen, and hydrogen come together. So a chemical change occurred to make the sugar from these ingredients or these elements. So a really big difference we can think about is the difference between these two things and when we put them together, what it makes. So elemental sodium, so sodium is Na. So elemental sodium, this metal explodes in water. So if you were to ingest sodium, it would explode you. So I would never tell you to go eat sodium metal because that's something that would be dangerous to you. So do not eat. And then elemental chlorine is a poisonous gas. This gas is actually a toxic gas used in chemical warfare. So sarin gas has chlorine in it. It's also what you make if you put bleach and ammonia together, so don't do that. But you also do not eat or breathe in this chlorine gas. Chlorine is Cl2 because it's diatomic. We'll learn a little bit about that later. When I put these two together, I get this, sodium chloride. So there's a big difference between these, right? One of them, one version of these things, both of them could kill you. And then this version of it, when you put them together, well, you actually need it to survive. You need sodium ions to survive. Those are your electrolytes. Yes, eat it. Now, of course, I know that if you're watching your sodium levels, you might, not have as much as someone else, but you do need it. If you don't have any sodium chloride in your body, your cells, your sodium ion channels won't work. So we have to have some. Sometimes we just eat too much. So kind of what does this look like on the molecular level? So you have your sodium metal atoms, then you have your chlorine gas atoms, and there's where I get that Cl2 from. It shows a what's called a diatomic element, and then when I put them together, they kind of are these ions now. So notice that these are neutral elements. So neutral atoms and molecules. And these are ions. So something happened to, what particle do you think can make something turn from neutral to an ion? Like, how do I go from sodium to Na+? What has to happen in order for that to occur? So sodium must lose an electron, must lose something negative to become positive, right? You don't gain a proton because then you're not sodium anymore. So let's think about the chlorine. So let's just think about chlorine as just one chlorine. It goes from chlorine to the chlorine ion or chloride. What has to happen for the chlorine to become -1? Well, it has to gain an electron. Where do you think sodium gets its electron? Where do you think this electron that sodium loses goes? And where do you think the electron that chlorine gains comes from? They come from each other. So chlorine is literally taking sodium's electron. And so that is creating these charges here. So it creates a special type of compound called an ionic compound where electrons are transferred and moved around. So all we have different between these two things that will kill you and this thing that you need to survive is the transfer of one electron. That's it. One tiny little electron makes a huge difference. So when we are talking about chemicals, if I say go eat some sodium and chlorine, that means I want you to like go explode and go breathe poisonous gas. But if I say go eat some sodium chloride, I'm concerned about your electrolyte levels. I'm probably being helpful. So notice the difference in that. I said sodium chlorine for the first part, and then I said sodium chloride for the second part. So naming and understanding how chemical compounds come together and how we name them and differentiate them is very important because it makes a very big difference in how you're communicating in science and in chemistry. So a compound is a little bit different than a lot different than a mixture. So we learned about this a little bit in chapter 3. So if you are a little shaky on that, you can go back into that video in chapter 3 where we talk about the classification of matter. And compounds are set ratios and mixtures are variable ratios. And I'll show you what I mean by this. Or variable ratios meaning that the ratios can change and it's still technically that mixture. So here you go. Here's a mixture of hydrogen and oxygen. It could be any ratio. It could be any ratio. So it could be a 2 hydrogen to 1 oxygen ratio. It could be 2 hydrogen to 2 oxygen. It could be 4 hydrogen to 9 oxygen. It doesn't matter. The ratio can be anything, and we would still call it a mixture of hydrogen and oxygen. So as a quick review, what kind of mixture would this be if it's in the balloon here? Yeah, it would be homogeneous or homogeneous because it's the same throughout. We're assuming the gases are all kind of like mixing around in there. But in water, your ratio is not anything you want it to be. So in water, you specifically have to have 2 hydrogens and 1 oxygen. If you try to do 2 hydrogens and 2 oxygens, that's no longer water. That doesn't work. So I can tell you a joke to help you remember this. 2 nuns walk into a bar, and because they're nuns, they're not going to drink. They're going to order something else. So the first nun says, I'll take some H2O. And the second nun says, I'll take some H2O2. And the second nun dies because she drank what? Second nun drank good old H2O2, hydrogen peroxide. If you're memorizing those polyatomic ions yet, you know that peroxide is there. That's the difference here. If I change my ratio, I'm killing nuns. So we have to be very careful when we're writing and naming chemical compounds to make sure that our ratios are set in a certain compound. Water must be H2O. It cannot be H2O2 or it is deadly. You use sometimes, I would say up to like maybe 6% hydrogen peroxide to like bleach hair. 30% hydrogen peroxide will burn your face off. So if she drank 100% hydrogen peroxide, like it just like burned her insides out. So definitely be careful of hydrogen peroxide, but I need water to survive. So it's these very small differences and things where you may feel like, oh, it doesn't matter if I write a 2 here or not. It does a lot when we're talking about the way that molecules and atoms are put together. So speaking of these formulas, I want to point out a few things about a chemical formula. So first we have our symbols, and these are just on your periodic table. And then you have your subscripts. And so these subscripts, like submarine, means under the writing, so the little writing underneath it. And that tells you how many of the previous thing there are. So H2O means there are 2 H's. If you don't have a subscript after an element symbol, that means just 1. So just like in math, I don't write 1x, I don't write 1s in chemistry. So I'll just put nothing there to indicate there's going to be 1 oxygen. Here's a more complicated chemical formula dealing with a polyatomic ion. A polyatomic ion is on a list of things that you're memorizing for this module. And so if you ever need more than one of these polyatomic ions, you must use parentheses around the polyatomic ion. And so what you want to indicate here is there are 2 of this nitrate group, indicating that there are 2 NO3s. So if I wanted to calculate how many oxygens are there in this chemical formula, how many oxygens do you think there are? So if I wanted to know how many oxygens there were, there are 2 groups of NO3. So there's 2 times 3, so there's 6 oxygen atoms. If I wanted to know about the nitrogen atoms, well, there's 2. And then no subscript means 1. So that's going to be 2 nitrogen atoms. And then there's no subscript for the Mg, so there's just 1 magnesium atom here. So we can kind of distribute anything inside parentheses with the number that's on the outside of the parentheses. Note here, do not put parentheses around only 1 polyatomic ion. So for example, if I wanted 1 hydroxide, I don't put the peroxide in hydroxide in parentheses because there's just 1. So you only need parentheses if you say, hey, I need more than 1 of these groups. So we can kind of dig a little deeper from our chapter 3 chart and really kind of see, well, now let's get more about these elements and compounds. So elements can actually exist in 2 different ways, atomic or molecular. And notice the difference here. Atomic elements exist as single atoms, and molecular elements exist as molecules, as groups of atoms bonded together. But if it's an element, it's still all the same atom. So be kind of careful with the molecular part, because you see we have molecular in 2 places here. If it's an element and it's molecular, all the atoms are the same. It's just that the same atom is bonded together. So it's not technically, you can't have just like, I mean, you can, but it's rare to find. You can't find in nature a single oxygen atom, because oxygen naturally bonds with itself and makes this kind of diatomic, or 2 atoms molecule. But then if you're dealing with a compound, we have 2 different types of compounds we're going to look at. Molecular, aka covalent. So you've probably maybe you've heard that word before. And then ionic. So ionic has ions or charges. And so the ionic compounds are held together by these attraction between positive and negative charges. And molecular or covalent are held together by chemical bonds. So they're sharing electrons. And so here we're going to kind of do a little bit more work on this. So here we have a sharing of electrons held together with a bond. So they're bonded together. And here we have that transfer of electrons we talked about with sodium chloride. So they're held together with an attraction between like a, I can't really use this color, so between a negative and a positive, and they don't actually touch. So I kind of don't like that they have this like touching. They don't actually touch each other. They just kind of are close to each other because they're just like very, very much attracted to each other. And you'll see that we call this a formula unit. That's a new word. It is the particle of an ionic compound. So the particle of a covalent compound is a molecule. The particle of an ionic compound is called a formula unit. So digging into these elements, so some elements just exist as atoms, like a mercury here. Mercury, you can break it down to a single atom, but for chlorine, it breaks down into a molecule. It doesn't really like to be an atom by itself because it's very unstable. So how do we know which atoms or elements are going to do this? You're going to memorize a list. So I want you to know these 7 diatomic elements. That means that they exist like this when they're by themselves. So they exist as diatomic molecules when they're not bonded with anybody else. When they're by themselves. Not bonded to anything else. And this is their natural state. This is their natural state. So if I just said like, oh, I'm going to breathe in some oxygen today, I'm talking about O2. If your patient, you know, have some oxygen hooked into like a ventilator or respiratory aid of some kind, you're talking about O2. You're not talking about just O, because oxygen just naturally exists as a diatomic molecule, as a gas. And so the rest of these are in the same kind of boat. You won't find just like a single atom of iodine in nature. You'll find only diatomic molecules of iodine. You can absolutely memorize a list like this if you want to. You can come up with a saying if you want to. One saying that I do know of is have no fear of ice cold beer. So that gets all those letters in there for you. Have no fear of ice cold beer. Have no fear of ice cold beer. That's one way to memorize them. I like this next method because anytime I can use the periodic table to memorize something, the better it is for me, because I always have a periodic table with me. So if you kind of look at where these are, they kind of make this certain shape, and the rule here is going to be 7. So the rule of 7. So we're going to start at number 7. We're going to make the shape of a 7. And then we're going to add one more, because if you count these, 1, 2, 3, 4, 5, 6, you need 7. So we're going to add hydrogen and let hydrogen play. So there's a total of 7. Start at number 7. Make the shape of a 7. Don't count an AT, just I. And then that's only 6. I need 7 to make this work. So add hydrogen as number 7. Those are your diatomic elements. Only write them as diatomic when they're by themselves. Or if I just say like nitrogen, that's N2. So we talked about this a little bit, but we're going to get into it a little bit more. The difference in ionic versus covalent compounds. And so the basic unit for ionic compound, again, is called a formula unit. And the basic unit for a covalent compound is called a molecule. Ionic compounds, electrons are transferred. In covalent compounds, electrons are shared. So electrons are transferred, ions are made. So ions are made and held together by their attraction, by plus and minus attraction. And then with your molecules, the electrons are shared in a bond. And that is what holds it together. And we'll talk more about chemical bonding at the end of this chapter. So you can look at some of these cartoons to get an idea of this, but sharing is caring. Caring starts with a C. Covalent also starts with a C. Sharing is also a covalent. So they're sharing, see how they're sharing these little electrons together? This is a bond here. So they're kind of indicating in this drawing that this is our chemical bond. We're sharing those electrons. And then sodium chloride, this drawing is a little bit off. It's not the chlorine giving to the sodium, it's actually the chlorine taking from the sodium. So if it would be better if the chlorine just kind of grabbed something from the sodium, but sure, it's still cute. This is a transfer of electrons. So we see a transfer, like a gift giving. Not really. It's more violent than that. It's more of a stealing, but sure, a transfer of electrons. So that when we finish this transfer, now we're both positive or negative charged, and we attract each other in that way. So again, more images just kind of showing what is happening here. These dots are electrons. If you remember from chapter 4, we talked a little bit about the dot structure, and I said we're going to talk a little bit more about this in chapter 6. Well, we'll talk about it a little bit later, but these dots are just the valence electrons. They're kind of showing you that some electrons are shared and some are transferred, and then you have this positive and negative, where M is a metal and in M is a non-metal. We'll talk a little bit about that in a minute. So what happens to my atom when I remove an electron? So here's kind of this model. I remove an electron, and notice what happens. What do you see happen to my size? This is kind of important. So the size of my atom, my radius, or atomic size, is going to get smaller. Well, because electrons are on the outside, if I take away something on the outside, it gets smaller. It's like taking off a layer of clothing, like a thick jacket or something. You get a smaller size, right? And notice, look at my electron configuration. So I go from 3s1 to 2p6. I lose that 3s1. So just whatever's on the outside is going to get lost as far as your basic elements go. So there are some elements where you have to be very particular about where you're losing them, but it's always from the outside that gets lost. It's the highest energy. And then you've got what happens if I gain an electron. So what do you notice about the change here? Well, I get bigger, right? So if I add on extra layers, it's going to get bigger. So if you add an electron on, you get a lot larger. And then you can see also where I added this on, 3p5 goes to 3p6. And you can see here that I kind of added that extra dot here, but I also added my charge. And here also, if you take away an electron, you have to decrease your charge or increase your charge by 1 because you are removing negative. So here are some ions that are hanging out in the body, what they do, why they're important. These are just important ions. These are also known as electrolytes. So ionic compounds can conduct electricity. So any ions you have in your body are electrolytes. So if you have not a lot of sodium or potassium in your body, your electrolyte counts will be low. You will probably wind up testing, in a annual physical or something, testing your patient's electrolytes at some point. And you'll be looking at the concentration of these ions in their blood and seeing, do they have enough of these that they need, because you need these to function properly. Your cells need these to function. Okay.